So section 4 deals with shape and geometry. So the shape of a molecule determines most of its physical chemical features. If it's double bonded, it's harder to break apart. If it's tetrahedral, it's probably easier to break apart. If it's big and long and chunky, it depends on how it's bonded together. So the shape of it is very important for its physical and chemical properties. So the geometry or the shape can be determined with, so VSEPR is the word that I'll just use all the time. VSEPR stands for valence, so we're looking at valence electrons. Shell, the outside, electron pair repulsion model. And what that does, it minimizes the repulsion of shared and unshared atoms. Electrons have what charge? Negative. Opposites attract, same charges do what? Repel. They don't want to be by each other. So any electrons that are in an atom don't want to be by each other. Which is why when we did orbitals, one would go in the one box, and then the next box, and then the next box. They want to be as far apart from each other as possible. They have the same charges, they repel. So electron pairs repel each other, and that's what causes the molecule to basically have the shape it does. The molecules are going to move out as far away from each other as they can. The unshared electron pairs, or lone pairs, can also help to determine the shape because they might push electrons a certain direction. And any electrons, whether they're paired up or not paired up, any electrons in a molecule are going to be as far apart as they possibly can. They are going to repel from each other. So we looked at our orbitals and our sublevels in an atom. Well, now we're putting atoms together and we're making molecules that are made up of many atoms. So when we do that, we get what's called a hybrid. We get a mix of something. So hybridization is a process in which atomic orbitals mix and form something new. It forms a hybrid. So if I have just carbon, my S2 would be full and my P2 would have 2 boxes full. Well, when I take carbon and I bond it with hydrogens, I get this hybrid that's called sp3. So instead of having these separate, this box basically moves up. I get a hybrid, and those electrons can spread out further. So what I want you to know is this. When you make molecules, we change things a little bit and we get a hybrid. We get something new. I don't expect you to fill out boxes like that, but I want you to know that we change it. It's kind of changed into something else. So carbon itself often undergoes hybridization because it can bond with so many different things. And carbon is usually going to form an sp3 orbital. Lone pairs can also occupy orbitals. Single, double, triple bonds are only going to form one orbital, or one hybrid. So what all of this is telling you is that anywhere I have a group of electrons, I'm going to have a hybrid. So if I have CH4, or whatever, CCl4, whichever, it does not matter. I am going to start with an S, so S, P1, P2, P3. This would be an sp3 hybridization. This has nothing to do with sigma and pi. CH4 has 4 sigma bonds, 4 single bonds, but it is sp3 hybrid or hybridization. If I have, let's take what? Let's take water. Well, no, because I'll have extras. Yeah, that's all right. So water, there's 2 electrons here. These would be my lone pairs. So this would also be S, P1, P2, P3. That would also be an sp3 hybrid because every pair counts. That would be sp3. If I have CO2, I have a double bond here, I have a double bond here, so they occupy 1, I would have an sp hybrid. The first, wherever you count the first group, it's always your S. Anything after that is going to go to P. Once you get to P3, you're going to go to D.
So you don't count the electrons, so like on the oxygen, you don't count the extra electrons on those?
Nope, you only count what goes around your central atom. So these ox, whatever's out on these terminal atoms don't matter. You only count what's around your central atom. And we'll practice those today. Here, table, I'll have you guys do this on review day. There's a page of this in your book. However, the cheat sheet that I gave you basically tells you the same thing, but it's a little bit different. But they do the same thing. I am not going to give you this as a cheat sheet. You're going to use the cheat sheet that I gave you. And then I'm going to skip that for now. And that's pretty much it. So I will do an example on the board next, but as far as note-wise, Vesper means basically that electrons do not want to be by each other. They spread out as far as they can. How can you use it to predict the shape? We are going to look at those hybridizations. Where do the electrons go? We'll use the Lewis dot structure that we've been using, draw a picture, and then figure out what shape that it has. And I'll stop there.